So the transformations are going to stay the transformations like they always were. Okay? So here's the exponential part of our graph. Okay? Yeah, sorry. It's graphing exponential functions, sorry. Yeah. It's just like a continuation of yesterday. So the 2 right here is our base. Okay? So instead of stuff being like underneath a radical or inside parentheses with a square, all of our horizontal stuff would be in the exponent, and then all of the vertical stuff would be multiplying in front or being added or subtracted onto the end. But all the changes before are the same. There still are reflections, compressions, stretches, and translations shifting back and forth. The difference is what the parent function looks like is going to be slightly different if this was a 2 than compared to if it was a 3. So it's going to benefit us in these ones to make a sketch of the parent graph first before we go about all of our transformations. So first look at this, and can anybody tell me like what transformations are going to happen? So basically our parent function would be the base just with the exponent of x. So the stuff that's causing transformations is all the stuff that's extra compared to that. So in this problem, the 3 and the negative. So how do those things affect our graph based on what we know about transformations from what we studied previously? Sorry? Good. Good. So vertically, what you see is what you get. You see a 3, stuff's going to get multiplied by 3. So that's a vertical stretch. Okay. Sure. Meaning those vertical distances are getting multiplied by 3. Okay. How is the negative going to affect our graph? It's going to be a reflection, vertically or horizontally? Vertically, because it's out there, which means it's going to go from like above to below. Okay. So there's also the vertical reflection. And remember, we're going to do all of our reflections before we do any of like our shifting. So we would reflect it before we moved it up or down vertically. Okay. In this case, we don't really have to worry about that, but just to make that note for future. So basically, we just need a shape to start with, and then we'll do these 2 things, and we'll have our final graph. Okay. So shape to start with. Look at the parent functions that we graphed yesterday. Y equals 2 to the x. Is it exponential growth or exponential decay? It's growth because the 2 is bigger than 1. The base is bigger than 1. Okay? Now, whether it was growth or decay, all the functions had 2 things in common exponential-wise. They had an asymptote here at y equals 0, and they had this point right here at 0, 1. Okay? But if it was growth, it was going to go up this way, like ours is. And if it was decay, it would have started up here and then come down towards the asymptote, if this was like 1/2 or 1/3. What we need is we need 2 more points besides this vertex point, because we know that this graph would be different if this was a 5 than if it's a 2. Okay? So some points that are easy for us to get, if you plug in 1, what's the point it corresponds to on this graph? So the point for this function is 1 comma what? Think about if you plug 1 in for x, what would you get for y? 2, because 2 to the first power is 2. Okay? They all have this point 0, 1 that we graphed. And then we need one other point. So you can either go with like 2, 4, or you could go with -1 comma 1/2. You might be thinking I'm crazy for wanting to involve negative exponents, but think about if 5 was our base in front instead of 2. So we'd get our 0, 1 point. If we plugged in 1, we'd get 1 comma 5. Would we really want to plug in 2? If 5 was our base, what would we get when we plugged in 2 as the exponent? 25. And that would be kind of ridiculous for us to try and fit on the graph, right? So if you want a couple reference points, for 2, it might not be bad to do this point up here, which would be 2, 4. But you may want to consider some things that use negative exponents. Remember, if you're using -1, all it's going to do is flip it over. It doesn't even raise it to a power. So you might want to use that point like -1, 1/2. Should definitely use 0, 1, and then the other points. Okay? So that's basically our parent function. What we're going to do with that function is we're going to reflect it, and then we're going to stretch it. Okay? So when we vertically reflect it, what's going to happen to the way our graph looks? It's going to flip over what? Okay, good. The whole thing is just going to end up down here below the asymptote or below the axis. Okay? So we would get, I'll draw it in two things so we can see each transformation. We would still have our asymptote here because we haven't shifted anything. Okay? But due to the reflection, our point 0, 1 would now be at 0, negative 1. And our point 1, 2 would now be at 1, negative 2. And our point negative 1, 1 half would now be at negative 1, negative 1 half. Okay? So that the curve is going like this. And this is what I'm going to ask you for point-wise when you graph these functions, because the parent function can be changed. Like they can change that 2 to a 5 or whatever else. I'm going to ask you to give me the vertex point and two other points. Okay? So just be aware of that. That's going to be a little different than last time because the graphs are a little bit different. All right, then we've done our reflection, so we're going to go ahead and stretch it vertically. Now, remember what that means. Okay? That means that what we're trying to do is take the result that we would have got and multiply it by 3. Okay? So I want you guys to take a second in your groups and decide what you think that's going to do to this graph. How's it going to look if we do a vertical stretch by 3? This group was asking me, how do you know what the vertex is? So this point right here, every exponential function has it, so we're going to kind of revolve around that point. But things are different now. That's not a true vertex in the fashion that things don't stretch and compress towards that point. That's really just another point on the graph. The reason I know that is think about if you plugged in points. Like let's say you were struggling and so you reverted just to back. Like I know I can plug in points and get stuff, right? Let's say we plugged in 0 for x and did the entire calculation for this equation. If you plug 0 in for x, what is 2 to the 0 power? 1. That 1 then gets multiplied by negative 3. So the negative part of it is causing the reflection, and times 3 means, is it still going to be here just one space away from the asymptote? Now it's going to be down here at negative 3. So what they're really getting stretched away from in this case is not a point. What are they kind of getting stretched towards or away from? The asymptote. Okay, so the asymptote is kind of like your reference of stretching and compressing now. Okay, things are getting closer to that or further away from that when we're stretching vertically. Okay, so this point too, you can see that it used to go down to negative 2. So we're going to measure this distance from the asymptote. It used to be 2 spaces away from the asymptote. Now if we stretch that times 3, it's going to be 6 spaces away from the asymptote. So it's going to end up here. This little one right here used to be how far from the asymptote? A half. If we take that half and multiply it by 3, we get 3 halves, which is really 1 1/2 away from the asymptote. So it's going to go like there. So our new curve is going to go like this. Notice that it looks a little bit steeper because we kind of took it and went like this. But is it okay with everybody, the point that we made, that 1, the parent functions are different if we change the base. 2, our stretches and compressions aren't being stretched and away from a point now. Instead, they're being stretched away from that asymptote that they're going towards or away from. Okay? Right? So a couple little different things. List of transformations, same idea. How we use them, slightly different. Okay? All right, so we listed our transformations. We got our graph. We found 2 other points besides the y-intercept. So our y-intercept here is at 0, negative 3. And now if we had to list these other points, we would say this point's at 1, negative 6. And this point is at negative 1, negative 1 1/2. The y-intercept, does everybody understand that 0, negative 3 is our y-intercept? How do you find a y? Let's say your graph gets like shifted over or something, so you didn't really graph the y-intercept. How could you quickly go back to the equation and find the y-intercept? Plug in what? 0 for x. Okay, a y-intercept always revolves on plugging in 0 for x. Remember when we did the investigation, the one point I asked you guys for was when x is 0, what is y? And you could just plug in 0 to find that. That's what you want to be able to do here. Okay? All right. So we listed everything we have to list. Any questions about this before we try one more? All right, so let's try another one and see if we can move it down a little bit. Okay, so let's talk about the transformations first. Then we'll give ourselves a little sketch of a parent function so we can transform those things onto the graph. Okay, so transformations. What do you guys think is going to happen here? Okay, so Ryan says there's a bunch of horizontal stuff happening here. I agree with him. Okay, and remember, just like before with the horizontal stuff, it's going to benefit us to look at it factored out. Okay, so this is all the horizontal stuff that he's talking about. Okay, so what kind of horizontal transformations are going to take place? So let's go through them. The negative, what's it going to do? Reflect. So there's going to be a horizontal reflection. The 3, what's it going to do? It either stretches or compresses. Which one if this is a horizontal shift? Remember, for the horizontals, you're going to multiply distances by the reciprocal of what you see here instead of exactly what you see. So I see a 3, which means distances are going to get multiplied by 1/3. Does that make things bigger or smaller? Smaller, which means is it a compression or a stretch? Compression. Okay, so this is a horizontal compression. Okay. All right, then what about this -1 in there with the x? What's it going to do? Okay, it's going to move it left and right or up and down? Left and right, because we're in the horizontal realm of things, right? Is it going to move it left or right 1 unit? Right. Okay, remember, all the horizontal stuff is crazy. You see 3, you multiply by 1/3. You see x minus 1, it actually moves everything to the right 1. Okay, so everything's going to get shifted right 1. And so now we've covered the negative, the 3, and the -1. We've covered all the horizontal changes. Okay? Then, are there anything multiplying in front or adding and subtracting at the end? Those are all of our vertical changes. So what vertical changes are going to happen here? Down 1. Is everybody okay with that? There's no stretch or compression in front like the last problem. There's no negative in front for a vertical reflection. So what we're seeing is just the -1 at the end, which is going to shift everything down 1. Yes, Ariana. So remember that the same thing as if you had like this function and inside of here was x minus 1, that the formula that we were given says x minus h, and the h number is supposed to be the shift right or left, but it already has a minus in the formula. So if the minus is already there, the h value here would be positive 1 because the minus is already part of the formula. Okay? So it's always the opposite of what we see when we're shifting horizontally. Okay? Vertically is always exactly what we see. -1 means down 1. But horizontally, x minus 1 means we're shifting to the right 1. Okay? All right. So we have all of this stuff, but before we can put it on the graph, we need to know exactly what this parent function looks like. And again, it's going to change based on any different numbers they put in here. Okay? So what is our parent function? Y equals what? What to the x? 2 to the x? No. What's the base of this exponential function? 1/2. That's why I'm saying they can change it. We're not always going to use 2 to the x. We're always going to use whatever base they picked, which means there's infinitely many of them. Okay? But we always know a couple things about them. Every exponential function, the parent function, when you just have a base to a power of x, has the asymptote at y equals 0, and it has the point 0, 1. Now, to know which way the curve goes, you need to look at this parent function and decide, is this exponential growth or is it exponential decay? Decay. Why is it decay? Good, because this number is less than 1, which means I expect the curve to go this way this time. Okay. Now, I need a couple other points besides the 0, 1 point for reference to help me graph. And again, I personally, and if you don't like this, you can choose other ones, but I would recommend plugging in the 1 and the -1 point. If you plug in 1, anything to the power of 1 is just going to be itself. So when I plug in 1, I'm going to get the point 1, 1/2. Okay. Anything to the power of -1 is just going to be the reciprocal of whatever is there. So when I plug in -1, I'm going to get the point -1 comma what? I have the point 0 comma 1. Did someone say -1 comma 0? If we plug in -1, think about what's 1/2 to the -1 power. Just 2. You're just flipping it over and that's it. So there's 3 points that we have for reference. So that's kind of our starting position. Then we're going to go through and do all of this stuff. So the first thing we're going to do is our horizontal reflection. Remember, do your reflections before you do your shifts and stuff like that. So our asymptote is not going to change with our reflection. Okay? If we're changing stuff from the right side to the left side and the left side to the right side, the point 0, 1 isn't going to change because it's right on the axis. And instead of having 1, 1/2, that point's going to end up reflected over here. Okay? And instead of having -1, 2, that point's going to end up being reflected over there. Okay? So this point's here, and this point's now here. So I have this just after the reflection. Okay? That's just our horizontal reflection. So now what's going to happen with our horizontal compression? Okay, but that would be vertical, right, if we're moving up or down? Taylor? Good. It's going to squish together by a third, and so now we need a horizontal reference point, right? Vertically, we decided it wasn't a point. Everything squished away or towards the asymptote. Okay? So what do you think happens here when we compress and stretch? What do you think things stretch towards or away from? So I heard asymptote, but we don't have a vertical asymptote to move in towards or away from. Okay? So any ideas? Towards the center point? Okay, so let's see if we just take this basic. So we've done the reflection. We have this part. So that's the reflection, and now we're trying to make sure that if we do this, everything just squishes towards the center point. So let's check if Taylor's right. If he's right, then if I've just done these two things, it's not going to change where this point is, right? If everything's supposed to squish towards and away from that. So let's think about if we plug in 0, okay, we get 1/2 to the power of 0, because 0 multiplies all that stuff out, and that would still be 1. So he's right. Even putting in a stretch or compression right here horizontally, that point doesn't change till you shift it. So he's right. Horizontally, we're coming all in or away from the 0, 1 point. Okay? All right, here's what I want you guys to do. Okay, so everything's going to squish towards or away from the point 0, 1. So we're going to move everything by a factor of a third. So this point used to be 1 unit away. Now it's only going to be a third of a unit away from that point. And same thing with this point that was 1 unit away on the other side. It's only going to be a third of a unit away. So we still have that point 0, 1, and the other points are only a third of a unit away. So that would be our graph just after the compression. The next thing we're going to do is move the whole thing right 1 and then down 1. So when we move everything right 1, all these points we just graphed are just going to be shifted. Okay, so see that everything's been shifted right 1 unit. Give us this. And then we're going to go ahead and shift everything down 1. So our asymptote is going to move down 1. Our point that's right here is going to move down 1. Our point that's right here is going to move down 1. And our point that's right here is going to move down 1. So then we have this exponential graph. Our asymptote then is at y equals -1. And the 3 points that we have here, we have this point, which now remember is only a third of a unit horizontally away from this point. So maybe it's easier to write this second point first. It's at the point 1, 0. This point right here that's only a third of a unit away from it would be at the point 2/3, -1/2. And this other point that's only a third away from it is going to be 1 1/3, comma 1. So we have our asymptotes. We don't have our y-intercept. It didn't end up being listed in our points. So we could go ahead and we can find the y-intercept by plugging in 0 for x in the original equation. So notice in the exponent, that's going to give us a 3. And 1/2 to the third power is 1/8. And 1/8 minus 1 is -7/8. So if I want to list the y-intercept here and I don't have it, I just calculated it. So my y-intercept is the point 0, -7/8.